Welcome back. So in today's class we will be learning about the dining philosopher's problem and its solution by using the semaphore. So you can see this particular diagram and some code I have written over here. Okay. So let us try to understand what is the dining philosopher's problem, and to get the solution for that problem we will be using the semaphore. So I have already discussed the semaphore in details in my previous videos. You can visit my previous videos and you can learn about the semaphore. So in semaphore topic I have discussed about the binary semaphore and also the counting semaphore, and also I have discussed one problem and the solution for the problem in the semaphore topic only. So you can visit my previous videos and you can learn about the semaphore in details. So let us try to understand this particular dining philosopher's problem in your operating system. Okay, so this particular problem, dining philosopher's problem, is only a what you can say is that this is being mentioned to make you understand how the synchronization problem in your operating system is getting solved. Okay, so synchronization, there are a lot of synchronization problem in your operating system. Okay, synchronization problem means to access the resource. A particular process wants to access the resource, and in that situation the synchronization problem arises, and their race condition comes, their deadlock condition comes. So all those situations, to avoid those situations, that means the synchronization problem, to avoid those synchronization problem, we are having the solution given by your operating system, right? So regarding that only we are going to discuss this dining philosopher's problem. Dining philosopher's problem, that means in the process synchronization there is some problem in the synchronization, that means accessing the resource. So we will be discussing practically means practical examples we will take and try to understand what is the synchronization problem and how to solve the synchronization problem by using the semaphore. So that is the only concept over here, that we are taking the dining philosopher's problem. Okay, so what the dining philosopher's problem says, that once upon a time there were 5 philosophers, and what is the work of a philosopher? They are thinking and eating. Their work is only that. Okay, so philosophers will be thinking a lot. Okay, philosophy thinking, and when they will be getting hungry and they will be going for eating, right? So once upon a time there were 5 philosophers, philosopher P0, P1, P2, P3 and P4. Okay, so these philosophers are there, and there is a condition, right? The resource that is available, just try to understand what are the resources, F0, F1, F2, F3 and F4, and there is a bowl of rice which is kept in the center of the table, right? So see, a particular philosopher can eat that bowl of rice by using the 2 chopsticks only. Okay, so they can access these 5 forks are the resources for the philosophers. Okay, so they are having sufficient chairs are available for sitting purpose. Okay, 5 philosophers, 5 chairs are there, one round table is there, one big bowl of rice is there from where they can take the rice and they can eat it. There are 5 plates are also there. Only problem is with the fork. Okay, the chopsticks that you call it. Okay, so you might have heard that in Asian countries like India, Nepal, Bangladesh, Pakistan, we used to grab the food by using the hands. Okay, so that is not the situation with the Western countries. They require the spoons, chopsticks and forks to eat their meals and all, right? So similarly, so we are discussing about the Western philosophers. Okay, so they require the chopsticks, and only with one chopsticks they cannot eat the whatever the meal they are having. They need 2 chopsticks to eat the meal. Okay, so that is the situation, right? So only the problem here is that the constraint over here is that they are having only the 5 forks F0, F1, F2, F3, F4. Forks means chopsticks, right? So they are having the 5 forks, 5 philosophers are there, but the requirement of the forks for the 5 philosophers is 10. Okay, so the resource required for by the 5 philosophers is 10. So 10 forks would be required, so that individual philosophers can access the chopsticks or the forks, each philosopher's 2 forks, and they can eat the rice easily, right? And they can quench their hungriness, right? So but here only 5 forks are there, okay, only 5 forks are there. So if situations are different here. So if 5 philosophers wants to eat the rice at the same point of time, then there the problem will arise. Okay, 5 philosophers, they require 10 forks, but only availability is 5, right? So the situation will be different. That means they will not be able to eat the rice at that situation. So I will take in case wise situation, 3 cases I will take, and I will try to make you understand how the synchronization will be happening properly, so that all the philosophers can quench their hungriness, right? So I will take the case number 1. First I will take the case number 1. So case number 1, in this I will try to discuss. So in the case number 1, think that all the philosophers are not hungry at the same point of time. Okay, so one philosopher is hungry, he wants to eat the rice. After completing, he will move, then the next philosopher will come, eat the rice. In a sequential way, they will be coming, eating the rice, and they will be moving. There won't be a problem. Okay, there won't be a problem. So where the problem arises, if 5 philosophers comes at a time and try to access the fork, which is not possible, and there the problem arises, right? So dining philosophers problem, that is the case number 3, as I said, where all the philosophers will be gathering together and trying to access the fork, and they want to eat the rice, but possibility will not be there. So at that situation the problem arises. That's why we are calling it as a dining philosopher's problem. And the solution is there. There is the solution for the dining philosopher problem is the semaphore. Okay, semaphore is the solution. So how the semaphore will give the solution for the dining philosopher problem, that we will be trying to understand. So case number 1, for case number 1, every philosopher will be coming at different time and trying to access the resources and take the rice. Okay, philosopher P0 will come, they need to access this particular code. Okay, so you know the semaphore is a variable which works with 2 atomic operations, that is wait and signal. So that I have already discussed in my previous videos. Okay, wait and signal. Okay, so each and every philosopher that wants to eat the rice, they need to access this particular code. Okay, so this is the entry section code, right? So this is the critical section, and this is the exit section code, right? So as you are already aware of this, right? So in this entry section code, they need to access these 2 lines of code. That is, each and every philosopher or the each and every process. Let us come to process and philosopher in a quite similar manner. Okay, so we will discuss, because we are discussing our computer system problem, synchronization problem, by taking the example of philosopher. Okay. So I'll say the philosopher and process at the same time. Alternately I will say, try to understand by that way, right? So each and every process, that means the philosopher has to execute the entry section, enter into the critical section, execute it and exit from the critical section, right? So each and every philosopher, if he wants to eat the rice, has to execute this particular 2 lines of code, then enter into the critical section, that means eating the bowl of rice, then exit from the critical section, right? So right now P0, in the case number 1, P0 wants to eat the rice, that means wants to enter into the critical section, right? So P0 will be executing this code, right? So wait chopstick I, that means he will be lifting the left hand. See, the condition is that they need to lift the left chopstick first, then lift the right chopsticks first, collect the 2 chopsticks and eat the rice from the bowl. Okay, so that is the condition. Left, right, getting together, eat the rice from the bowl. Okay, so that is the condition. Let us first try to understand the case number 1. So case number 1, that means each and every philosophers will be coming in the different timing. Okay, different timing, not at a time they will be gathering to eat the rice, right? So first of all P0 will be coming, then P1 will be coming, P2, P3, P4 in a sequential way they will be coming, eating the rice and they are moving out. Okay, so that is our case number 1. So P0 first of all wants to eat the rice, so it needs to execute this particular code. So wait chopstick I, that means it will be picking the fork F0. Okay, so fork F0 it will be picking, then another line it will be executing wait chopstick I plus 1, that means 1 plus 1 2 mod 5, that means what is the result? 2 forks are there, right? F0 picked, F1 it will pick, right? So that means 2 forks, 1 plus 1 2 mod 5, what is the result? 2 mod 5 or 2 percentage 5, the result is 2, right? So the 2 chopsticks are in the hand. Now P0 can enter into the critical section, right? So enter into the critical section means it will he will start eating the rice, right? So after quenching its hungriness, it wants to come out, that means it will execute this exit section, right? Signal chopstick I, it will put the fork F0 in the left hand side, then signal chopstick I plus 1, it will put the right chopsticks, put it in the table, that means F0 and F1 will be putting in the table where it was, then it will be exiting out. Okay, that means he will be doing his usual work. He has quenched his hungriness, then put both the chopsticks down in the table, then starts its philosophy activity, that means thinking. Okay, right? So P0 has completed its eating, right? So now P1 wants to enter, wants to eat the rice, then what it needs to do? P1 comes, execute this particular line of code, that means wait chopstick I, that means P1 wants F1 and F2, F1 is already available, P0 has already completed his eating activity, he has completed and he has put back the fork in the table. Now F1 is available, so for P1 it's not a problem, F2 is also available, so it will execute wait chopstick I, that means F1 it will pick, then wait chopstick I plus 1, that means 2 mod 5, then 2 chopsticks, that means F1 and F2 is in the hand of the P1 and it will start eating the rice. So when it will complete eating the rice, it will execute this particular exit section, signal chopstick I, put the F1 in the table, a signal chopstick I plus 1, that means 2 chopsticks are there in the table. P1 complete. Likewise P2 will complete, execute this code, complete its eating activities, exit section, over. P3 likewise, P4 likewise, all the philosophers will be successfully eating the rice, there won't be any kind of problem. This is the case number 1 that I discussed, right? There won't be a problem. In a sequential way they are coming with their understanding, they are eating the rice and they are moving out, so there won't be a problem. Okay, so this is the there is no problem in the dining, right? Case number 2, let us discuss the case number 2. So in the case number 2, so just try to understand. So what we will be doing that for 5 chopstick we will be giving the semaphore value. Okay, so for example, F0 is S0, F1 is S1, F2 is S2, F3 is S3, F4 is S4. So we are having the 5 semaphores, right? So S0, S1, S2, S3 and S4. So each and every semaphore is being initialized to value 1, right? Is initialized to value 1. Okay, so right now the philosopher P0, okay, P0 wants to eat the rice. So philosopher P0 wants to eat the rice, then it will execute the which semaphore? Wait, semaphore S0, right? So it will execute the semaphore S0 for accessing the fork number F0. Okay, so understanding this index value that is F0, you try to understand, right? I have kept the same one for S1, F1, for S2, F2, S3, F3, S4, F4, right? So right now P0 wants to eat the rice. Right now what it needs to do? It needs to execute the semaphore S0. So it needs to execute the semaphore S0. So what is the semaphore value of S0? 1, right? So it will be decrementing wait, it will be executing this wait, right? Semaphore S0. So it will be decrementing the semaphore value to 0 and it will be picking, P0 will be picking the fork F0. Left hand side fork he has picked up, right? So right now this execution has been completed by P0. Now he needs fork F1. So it will, in the second line of code, it will be executing the semaphore S1, right? So when it will be executing this line of code, the S1, it will be decrementing the semaphore value of S1 from 1 to 0 and it will be getting the fork F1. So for P0 there won't be a problem, right? F0 and F1 he got and he starts eating the rice, right? So right now P1 wants to enter. Now P1 wants to enter to eat the rice, right? Philosopher 2 wants to, P1 wants to access the eating process, right? So he wants, he comes and sits in his table and he wants to access the fork and he needs to execute this particular code right now. So right, so P1 right now wants to enter. So P1 will be executing this code. Wait, chopstick I. That means he wants to execute. P1 has to access the fork F1. That means semaphore S1. So semaphore S1 is already 0. Right? The semaphore S1 is already 0. So P1 will not be allowed to enter into the table. From here only it is getting blocked. Because semaphore value of S1 is already 0, which is made by the P0. That means P0 is eating the rice. So P1 will be getting blocked and P1 will not be allowed to eat the rice. Okay, so are you understanding? So right. So from here in the first line of the code only P1 is getting blocked. Right. So right now P2 wants to enter and access the table. So can P2 enter? So for P2, what is the fork required? F2 and F3. That means semaphore S2 and semaphore S3. Okay. So semaphore S2 and S3 value is 1 1. So P2 can enter and access the table. right? So right now P2 execute this code with chopstick I, that means semaphore S2. So thereby decrementing the semaphore value from 1 to 0, and it will be P2 will be able to pick the left hand side chopstick, right? So S2 and again right hand side chopstick, decrement the semaphore value from 1 to 0, execute this line of code also, and able to access both the semaphore and entered into the critical section, right? So now P2 can access the critical section, that means eat the rice. So here you can see inside the critical section two processes are already there, two philosophers are already there, right? So because there are independency are there are a lot of instances are there, so that's why in a critical section two processes or the two philosophers can execute simultaneously. Here the mutual exclusion is not satisfied, right? So what usually happens that for a process synchronization mutual exclusion has to be satisfied, right? Mutual exclusion means when a process enters into the resource, it has to acquire that resource until it completes its execution, then coming out, then enter another process to access that resource, right? When it completes only it can come out. That is the mutual exclusion. That means a process is holding the resource in a mutually exclusive way. So see, mutually exclusive, here that is satisfied? No. Here that is satisfied? No. Mutual exclusion is satisfied because two processes are inside the resource, P0 and P2. It can be possible, right? It can be possible because here the resources are independent to each other. There are different instances are there. As I have said that global variable, if they are having two processes can enter at a time, if there are various instances are there, that means they need not be they should not get collided inside it. If collision happens means the problem occurs, synchronization problem occurs, right? So here the collision collision cannot happen over here because they are independent with each other. That understanding or not? So P2 requires fork F2 and F3. P0 requires fork F0 and F1. So no collision. They are independent with each other. So in this situation, even though the mutual exclusion is not achieved, process synchronization is happening. Right? Understanding? So P2 can access, enter and access the resource. Right? So this is the case number 2. So any other process can enter P3. If P3 wants to access, it requires which one? S3 and S4. But S3 is already 0. Semaphore value is already 0. So P3 cannot enter. P4 can enter? No. P4 also cannot enter because it requires F0 and F4. That means S0 and S4. S0 is already 0. So it also cannot enter. Right? Right? So no other philosophers can enter and access the resources, right? P0 and P2 can only enter and access the resources. Okay, so that is the situation in the case number 2, right? That means P1, P3 and P4 are not allowed to enter into the critical section. That is the concept, right? So at a single given point of time, only two processes can enter into the critical section and access the resource. Okay, so that is the point over here, right? So it doesn't mean that P0 and P2 are the only processes that can enter into the critical section. So it can be your P1 and your P4 also, right? So it requires different resources. P1 requires F1 and F2, P4 requires F0 and F4. So that also can possible, right? So at a given point of time, only two processes can or two philosophers can access the resource. So this is the case number 2, right? So let us move to case number 3. So let us take all the semaphore value as 1, right? So try to understand the different kinds of situations, right? So is there any the semaphore is it giving the solution for different kinds of situations or not? Okay, so that we are trying to understand in different kinds of situations. First situation, in case number 1, I said that individual philosophers will be having the different timing in a sequential way. They will be coming and accessing the resource. They can achieve their target, and they will be quenching their hungriness. In case number 2, if all the philosophers wants to access the resource, it is not possible. Only two philosophers can access the resource at a given point of time. That is the case number 2. So in the case number 3, for example, see different kinds of situations, right? So case number 3 situation is there. All the philosophers are coming together, like in the case number 2. Here also in the case number 3, for example, all the philosophers are coming together. So philosopher P0 is coming and he wants to access the resource. What the situation happens that P0 is picking the left hand side resource, that means S0. It is picking the left hand side, and in that situation, okay, so P0 comes, it will execute this code, right? So P0 comes, it will execute this code with semaphore S0, right? Semaphore S0 decrementing the semaphore value S0 to from 1 to 0, thereby picking the fork F0, right? So in that, when P0 executed this line of code, what happened that due to some problem, it gets printed out. Okay, for example, this P1 wants to enter into the resource, and for example, P1 is a high priority process, high priority philosopher. So P0 has to be getting printed out due to several reasons, right, in your computer system, right? So P0 has to be printed out. So it has executed only one line of code, that means picking the fork F0 only. Picking the chopstick, only one chopstick, left hand side chopstick, right? So S0 it has picked, thereby decrementing the semaphore value from 1 to 0, and it is not able to access the semaphore value, semaphore S1, because P0 has printed out and P1 wants to execute, right? Trying to understand? That means with P0, which fork is there? Only the F0 is there, and it could not access the F1. Okay, left only picked. So for a philosopher to eat the bowl of rice, 2 forks are required. Only one fork only he has picked up. Second fork not able to pick. At that time, P1 has come out. P1 wants to enter into the table, right? So P1, what it does, that P1 execute this particular line of code, that means where your semaphore S1, right? Semaphore S1, that means the fork F1, right? So fork S1, right? So thereby decrementing the semaphore value from 1 to 0, and the situation same happens over here. It is not able to execute the second line of code, and P1 gets printed out. That means it could not access the fork F2, that means semaphore S2, right? This situation. So right now P2 wants to enter into the critical section, and P2 executes this particular code. By executing this particular code, wait P2, right? So left hand side, which was left hand side? F2, that means S2, right? So he wants to pick the first left hand side. That is the condition I said you in the beginning itself, right? It has to pick the left hand side, then right hand side. That is the constraint, right? So it will pick the left hand side S2. It will execute the semaphore S2, this particular line of code, thereby decrementing the semaphore value from 1 to 0, and P2 also gets printed out. It is not able to access the S3. It requires the S3, but it gets printed out. Right now P3 wants to access the resource. So P3 what it does? Executes this particular line of code, right? P3 executes the S3, right? Wait semaphore S3. So thereby decrementing the semaphore value from 1 to 0. Okay, and right hand side S4 it is not getting executed. So P3 also getting printed out by executing this line of code only. Okay, so P3 got access the S3 only. That means the fork number F3. So he could not access the fork number F4, right? Understanding? So right now what happens? Process P4 wants to access the resource, right? So what it will execute? Process P4 will be executing the semaphore S0 and S4, right? So which one is the left hand side? F4, that means semaphore S4. So it will be executing S4, then S0, right? So S4 it will be executing the S4, right? So P4 wants to execute this line of code executed. When it executes this line of code, that means wait semaphore S4, thereby decrementing the semaphore value from 1 to 0. And not able to access this line of code because S0 is already 0, right? See the situation, see over here. Each and every philosopher has accessed their left hand side fork, and the right hand side fork is unable to access by the individual philosopher. So in this situation, so this is the questions asked in UGC NET, your gate level questions, right? So try to understand properly. See, in this situation, there is any chances of getting out of this situation? See, the deadlock situation arises over here. Okay, so what is the deadlock situation here? See, each and every philosopher has accessed the left fork. They are unable to access the right fork. Thereby, every philosopher, all the 5 philosophers are unable to eat the rice. The rice is already there, but due to the deficiency of the fork as a resource or the chopstick as a resource, they are unable to eat the rice. The ultimate aim is that critical section is eating the rice, but they are getting stuck over here, and this will be continued in a long period of time. If this happens for a long period of time, then the deadlock situation got arised here. That means all the processes will be getting blocked and they will not be able to access the resource. Okay, so it seems that all the processes are dead. Okay, dead means dead due to lock. Okay, now we say it as a deadlock. Okay, so all the process of 5 philosophers are unable to access this particular resource. So this is the deadlock situation happens. So is there any solution given by the semaphore in this case number 3? Is there, if such situation happens, is there any solution to overcome this particular situation? Yes, there is a solution. Okay. See, what is the solution? Solution is that this particular process P4, if you will reverse the code S0 and S4, then we can get the solution. Okay, so if you are reversing this particular code, that means the last philosopher. Okay, so only, okay, so if there is n number of philosophers, then n minus 1 philosophers can access the code in this particular way, and the last philosopher, that is nth philosopher, can access the code in a reverse way. If you are reversing the code, then that means this one you are making it in the beginning and this one in the down. Okay, so if you are reversing the code, then solution can happen. So how? We can get the solution by reversing the code. So the last process P4, so if we are making S0 S4, so right now P4 wants to access this particular resource, then P4 will need to execute this particular code. So P4, when it executes this particular code, where chopstick I, that means semaphore S0. So when it finds the semaphore S0, right? So S0 value is already 0, right? So when the semaphore value is already 0, so this particular process will be getting blocked. It cannot process, last process cannot enter into the critical section, right? Cannot enter into the critical section, so P4 is getting blocked, right? So all the 4 processes have entered into the resources with only one resource, one fork or one chopstick, and on the right chopsticks they didn't get it, and process P4 is totally blocked. It is not allowed to enter into the resource by just reversing the particular code. Then the previous one, reversing it, right? In that way, we can get the solution of the dining philosophers problem in case number 3, right? So how? See, P4 is got blocked. Now P3 wants to execute, means what was the deficiency of P3? It could not access the semaphore 4. It could not access the fork number F4. So right now P3 has already executed S3, left hand side fork is already there. Right now S4 it can execute. Yes, it can execute because the semaphore value of S4 is 1, right? So right now P3 will be executing this particular second line of code where chopstick I plus 1 your mod 5 it can access the right hand side chopstick also. That means the semaphore S4, right? So it got the left hand side, right hand side, right? Left hand side and the right hand side, that means S3 and S4. So it got both the chopsticks, it will enter into the critical section. That means so P3 can access the resource because the semaphore value or the S4 value is already it is 1. So it will execute this particular line of code, the second line of code, access the S4, that means pick the right hand side fork, that means S4 means your F4, it will pick both the chopstick it will get. Okay, so to pick that it will execute this particular code, thereby decrementing the semaphore value from 1 to 0. Take the right hand side fork, okay, this and this both fork it got, execute, enter into the critical section, eat the rice by process P3 or the philosopher P3. After quenching its hungriness, it will come out by putting both the fork. For doing that, it needs to execute this particular code, right? So signal here S3, signal S4, right? Signal S3 and signal S4. So thereby incrementing the semaphore value of S3 from 0 to 1, signaling the semaphore value of S4 from 0 to 1. So P3 has completed its execution, right? Now P2 wants to enter into the critical section. It has already in the critical section, it has acquired the S2, but S3 is the right hand side fork it was not getting, right? So right now P2 can get the right hand side fork. Yes, it can get, because the deficiency was only S3. So what is the semaphore value of S3? Is already 1. So right now P2 also can execute the second line of code. Okay, so acquire the S3, that means fork F3 and enter into the critical section, right? So thereby decrementing the semaphore value of S3 from 1 to 0 and executing this particular code. Then enter into the critical section, eat the rice, then it will execute this this particular line of code and come out, right? So that means this line of code signal your chopstick which one? Your S2 and S3, right? S2 and S3. So signal S2 thereby incrementing the semaphore value from 0 to 1, and S3 thereby incrementing the semaphore value from 0 to 1, right? So right now P2 also has completed its eating, right? So now P1 wants to enter, it can access the resource. Yes, it can access. See, S1 it is left hand side, S1 is already it has acquired. Now the requirement was S2, right? So that means fork number 2, F2, right? So right now it can access that S2. Yes, it can access, because semaphore value is 1. So it will execute this second line of code, take the semaphore value, by decrement the semaphore value from 1 to 0, enter into the critical section, eat the rice, execute the exit section, come out, right? So right now P1 will release the fork S1 and S2, okay, thereby by executing this signal S1 and signal S2, okay. So thereby incrementing the semaphore value from 0 to 1 S1, from 0 to 1 S2, okay. So right now P1 also completed its eating activities, right? Now P0 can enter. Yes, it can acquire the right hand side fork, that is S1, because the semaphore value is 1. So it will execute this second line of code, acquire the fork, thereby decrementing the semaphore value from 1 to 0, enter into the critical section, eat the rice, execute the exit section, right? So signal S0 S1, thereby signal S0 S1, right? So thereby incrementing the semaphore value of S0 0 to 1, semaphore value of S1 0 to 1, right? So right now P0 is also completed its eating activities, right? So right now which one is left out? The P4 was blocked because of reversing of code to have the solution, right? So now P4 can enter and eat the rice. Yes, it can enter and eat the rice, right? So P4 will come, which was blocked at the last. It will try to access the resource. It can easily access the resource. So P4 will come, execute S0 S4. Okay, so S0, what is the semaphore value of S0? 1, right? So lastly P4 will come, execute this by decrementing the semaphore value from 1 to 0, accessing, right? Then S4. S4 it can enter, yeah, wait, semaphore S4, so semaphore value is 1, it can enter. So by decrementing the semaphore value from 1 to 0, right? So P4 enters, execute the critical section, eating of the rice, completed, executes this signal operation. Signal S0, signal S4, thereby incrementing the semaphore value from 0 to 1. So P4 also completed its eating activities, right? So in this manner, by changing a code, that means by changing the code, that means if there are n number of philosophers, that means n number of processes, then n minus 1 number of philosophers or the processes can execute the same line of code. The last philosopher of the process has to just reverse the code, then we are getting the solution for the dining philosopher's problem. The same solution is there in your operating system for process synchronization. Okay, so by using the semaphore in this manner, we can achieve the process synchronization. That means your starvation, race condition, deadlock condition is avoided. Right? Understood? I hope you understood the dining philosopher's problem dining philosopher problem and its solution by using the semaphore. And I have shown you the 3 cases, case 1, case 2 and case 3. I hope you understood very well. So we will be meeting in the next class. For the time being, thank you. So if you haven't subscribed my channel till now, you can click the subscribe button. If you want, you can like the video, share the video if you have understood the concept in a very clear manner. So for the time being, thank you. Namaste.